Okay, live stream is running. Hello guys, time to start. It's still pretty crowded in here. Could everyone find a seat at least? Or in the row after the last row? I hope we can manage with the room. Yeah, what are your feelings? Is the room okay, or is it worth asking for a bigger room? So asking for a room change always might trigger a change of the slot again. Usually you end up with something less favorable than these afternoon slots after changing late in the game. I'll wait for your strong opinions either direction. That's today's code for, our little game of checking that you're here. And this is where we'll go to in a second. But we have to finish off with a last bit of the proof techniques session. That's the last bit of the section on correctness proofs. We talked through what formal verification is and how you can prove termination, that a program stops eventually. And then we talked about loop invariants as one piece of the Hoare calculus, if you know what that is, for proving pre-post conditions for programs. And the key bit are the loop invariants. So to recap that, we have a little piece of code with a while loop in it. We would like to show something after the loop, because that's what the loop computes. We would like to prove something about the state of the program after the loop. And we can make assumptions for getting there before the loop. But then the trick is, what can we say inside the loop? Because this is repeated many times. So the state keeps changing. And hence, we need a little bit of a trick here, if you like. And the trick is to find a statement, a Boolean formula I, called the loop invariant, that satisfies a few conditions. Most importantly, it needs to include what we want at the end. But it has to be so that it holds before the loop, and it also holds inside the loop with slight additions attached to it. So let's see an example of such a proof on this code, which finds the maximum of an array in the obvious way. You step through it, and you keep track of a maximum of a prefix of the array. That's intuitively what the code does. For a formal proof, we have to find a loop invariant. So I've already done that job for you. And the loop invariant consists of two parts. It will be useful to give them colors. I hope that these are distinguishable no matter what kind of limited color side you might have. So this is a little lighter than the other one, right? Is red and blue, in case that helps. So the first thing we have to check, we have to go through these three conditions and show that each is satisfied with the loop condition that we've chosen. The first condition says the loop condition holds before the loop. So I marked in the code these 4 positions, A to D. So let's have a look at this first part. If we look at position A, we've just initialized things so that I is 1. So if you look at what the loop invariant really says here, I'm just copying this and insert what the value of I at this point is. I mean, this takes a lot longer to write than to think through. If you put I minus 1 here, so this is just 0 up to 0. It's the set with just the 0 in it. Well, the second bit is not very interesting if we insert 1 here. 0 up to 0, it's the set with just the 0 in it. Well, the second bit is not very interesting if we insert 1 here. 1 up to 0, it's the set with just the 0 in it. Well, the second bit is not very interesting if we insert 1 here. 1 up to 0, it's the set with just the 0 in it. That's something that we assumed in the loop. So we call the function with an array that has at least one element. And so that part is what guarantees this first bit. I should have done this in red, I guess. Sorry, light blue. I'm not that colorblind, but so that guarantees the first bit of the loop invariant just by assuming it at the beginning of the function. And that's something you often have to do. Now for the second bit, we can just rewrite this. So the second bit, that maximum doesn't really do anything, right? It just insert this. It takes the maximum over a set that contains a single value. So the maximum will always be that single value. So all we're saying here, this part on the right is really just a of 0. So the claim that we're making is the current max is the value of a of 0. And that's exactly how we've assigned it just before that. So that's also fine. Okay? So that was the somewhat easy bit because it didn't really involve the loop yet. I'll try to have the code on the slide as well as my writing. It's going to be a bit of a challenge. For the second part, we need to show that the loop invariant and the condition of the loop, so that's this fact that I is strictly less than n, these two things together at B guarantee that we have, again, the loop invariant at C. So that's an implication, right? And we talked about last time at length how you can prove, how you can possibly prove implications. We talked about all these different proof templates and so on. So that's applicable here. Now, in this case, the most convenient bit is to do a case distinction first. And the reason for that is that inside the loop, there's an if. So there's really two things that can happen depending on whether the if is taken or not. So it's quite natural that we want a case distinction based on whether or not this loop condition is, this if condition is true. And we'll look at those two cases separately. So a first case would be that this is true. Which means intuitively that we found a new minimum, a new maximum. Right? So the new element we're looking at, we're taking into account now, is bigger than what we currently had as the maximum. Now at this point, we use what we had in the premise. We're proving an implication, so we can assume what's on the left side of this implication arrow. In particular, we know that at the position B in the code, here, the invariant I was true. And conveniently, that's just after where we, just before where we are in the code now, if we're looking at this if. So using the red part of the loop invariant, we can use what we know about current max. Namely, that current max so far is the maximum of this expression, like just up to I minus 1. If we're in this case, then the if statement is true and the then branch is executed. So we assign current max and we set it to a of I. Now, what does that mean for this red statement of the loop invariant? We can already have a look at that. Let's start with the maximum. What that means is I can now extend the range of this maximum in the loop invariant for one more index, and it will still be true. Because we've seen the current maximum, so the maximum of the elements up to position I minus 1, that was current max, but AI was even bigger. So clearly AI is the maximum of everything up to position I. It's just rephrasing this again. This is almost like the next loop invariant that we need, except that we're not yet at position C. Instead, we've only executed line 9 so far. So what happens in line 10 is something that changes the value of I. We make I1 bigger. So that means in the loop invariant, we have to adjust the value of I. If this was true before, then if we now make I1 bigger, we have to make it in the statement 1 smaller to compensate for that. So this, again, this is true at or after line 9. And so once we set I to I plus 1, we'll have the same thing, but with an I minus 1. Because this is now actually one bigger, okay? And now if you look at this, that is exactly the red part of the loop invariant. It's character by character the same thing. And also after line 10, I mean, should have stressed this, that's really at C. It's the same position. So that in that case, so that's often how a proof goes. So zoom out a bit, right? We're proving the second part of our overall claim, and within that claim, we're in the first case of a case distinction, and within that case, we've proven that the red part of the loop invariant holds again at the bottom of the loop body. So next, the blue part. What can we say about the blue part? We know at B that the loop invariant was true, but we know more. We also know that the condition was true. So the loop condition, otherwise we would have left the loop. So at this point, I was strictly less than n. The loop invariant only says less or equal, so this strictly less is stronger. I don't know. I'll mark this with red and then mark this with blue. I don't want to write it in blue because the contrast is not that great. So this was true at B. Actually, no matter what happens in the if statement, that doesn't touch I, but we'll always increment I afterwards. So by the time we get to C, we'll have made I 1 bigger. So we can only say that I minus 1 is less than n. But that still implies that I is less or equal n because it's integers. And so that finishes the blue part. And I think we can move this outside of the case distinction because it's the same for both cases. So I'll move this down here and out of the case distinction. We have to do our case 2 though, which was that the if statement is false, right? This one. In other words, a of I is not bigger than the current maximum. In that case, we don't execute the if statement, right? But we still have to argue for the red part to be true at the end of the loop. So we don't touch current max. However, we know something. We know that the previous maximum is at least as big as this next element. So we can again extend the range of the maximum by one more element. So from this statement, we know if we take our maximum and go from 0 up to including I, then that is still the value of current maximum. We haven't changed it. It's fine if we have this tie, if the next element is another occurrence of the maximum. So it's fine, we can still pick the first one. And the rest is really by the same arguments. So this is after line 9. And so after we incremented C, I, we do the same step. Let's say the red I holds. At C. Okay. Notice that we're basically following the structure of the code, but we're also following the definition of a maximum. It's either if you add one more element, either that element is a new maximum or it's not. That's all that happens. So that finishes the proof of the red claim in both cases of the case distinction. And we could get rid of the case distinction for the blue part because it behaves the same in both ways. Taking those two things together, that proves that I holds at position C at the end of the loop body. Okay? And that was this part. So that finishes. I could have ticked this off. We've done that here, done that now. What's left is the Roman third, which is that the loop condition actually does what we want for the post statement, for the post condition. And for that, it's basically sufficient to spell out what that is. And I'll spare you another round of me typing this, copying it. So that's the 2 bits of I, but then we also have not the condition. The condition was that I is strictly less than n. So not the condition is I greater equal n. Mark that here. Okay, you remember? And so if you look at this, I copied the wrong thing here. This was from condition 0. There's no point if you can't read it, right? So if we're at this point, then we take the last 2 conditions Okay, again, shouldn't have copied this. This was an I. I inserted the 1 there. These two things together obviously mean that I is equal to n. And then if you insert n in here, you get the statement that current max is the same as taking the max over the entire array, because we're letting k go from 0 up to n minus 1. So this is true at the end of the code, and intuitively that's what we wanted, because that's the maximum of the array. Okay? That's what mathematicians do. They draw this little quad-erat demonstrandum box at the end of the proof, just to look fancy. Okay, any questions on this before we jump to Unit 1? If I remember correctly, there was there was a question on Slido, I think, which is best handled on Campus Wire. And good. Questions on this so far? Yeah.
Every algorithm we ever write just like this?
We won't do it for every algorithm, so we won't get that far.
For example, like some exercise or some task, do we need to prove like this?
You'll do an example in the tutorials where it's explicitly stated that you have to go through the details. And then for later exercises, you will not go all the way down usually. Some higher level English language argument why it's correct will be enough. The only problem with that is that it's easy to fool yourself. So if you're not completely convinced yourself, it's good to be able to go one level down. Okay, if there are no more questions on the proof techniques, we'll leave that behind us for the moment and jump to the next unit. So welcome to Machines and Models. That's Unit 1 of COMP526. Where we'll talk about the basic mathematical abstractions that we'll use for our algorithms. The learning outcomes are stated here. Just to briefly summarize this, we'll talk about analyzing algorithms. So when the last unit was a bit about proving to ourselves and others that an algorithm does the correct thing, then this unit is more about, does it do it fast? Because there are many problems where getting the answer in some unspecified time is as useless as never getting it. We'll talk about the random access machine model and the big O classes. And we'll check on a few examples how we apply this. There will be more examples in the later units for specific topics and algorithms. It's an algorithms class, but I haven't really defined algorithms so far. So at least in week 2, we should do that. I'll go basically by just a simple intuitive explanation. Algorithm is a sequence of instructions. And you can think of that as similar to a cooking recipe. But there's a few points where the analogy is a little breaking down or needs a bit more of clarification. First of all, as anyone might have noticed, if you get passed down some recipes from your mom, it's sometimes not clear what one step really means. And we don't want that for algorithms. Everything has to be so clearly defined that a stupid computer can execute it. We also insist that the program that's making up an algorithm is finite. So you can't have, oh, now let's distinguish all possible cases, and I'll just list them all. If there's infinitely many of them, that doesn't count as an algorithm, because you could never finish writing it down. You could never feed such a program to a computer. Now, what I've said so far is basically just telling you what a program is. An algorithm, on top of that, should be a solution to a general problem. So instead of just computing some specific example, it should work for a whole class of problem instances. If you want, think of it as not adding two specific numbers, 17 and 4, but being given two numbers without knowing in advance what that number will be, you can add them up with your algorithm. That's the distinction. It's a little, wow, if you look at it too closely, it's maybe not so clear what this means. You can formalize this further, but I don't think it has benefits for us. The algorithms in our module will always have this input-output abstraction. So you get certain things as an input, then your algorithm does things with them and produces an output at the end. If you want a more typical example, apart from just adding two numbers, you can take a sorting algorithm. For example, bubble sort is maybe the simplest and most well-known because it has a funny name and at least it's easy to specify. Another thing here that I want to make clear, the distinction between an algorithm and a program can sometimes be a bit fuzzy, but what we think of as an algorithm is usually a core idea that makes up how the thing works. Like in bubble sort, this bubble operation means you look at two consecutive things, and if they're out of order, you swap them. And then you basically say cook until done. Repeat this until nothing more happens. Or you can say it a little more precisely. Go from left to right and continue doing that until nothing ever changes anymore. And there's twists to that, all of which we would say that's still bubble sort, but there could be 5 different programs that all look slightly differently in the details. But we want algorithms to mean something slightly more abstract. Again, this is an idea that's hard to grasp because it would mean to define what is abstract enough. I think in the examples that we talk about, you will usually have no problem distinguishing a concrete program from the algorithm, from the algorithmic idea. We'll mostly talk about algorithms, but we'll also talk about data structures. So what's a data structure? Question? Pardon? Speak up. Okay, I will put them up after class. Yeah, apologies. I think I promised to put the slides up in advance. I think I just forgot for this. I didn't make any last-minute changes. Could have just uploaded them. Yep. Yes, you can always look at last iteration. There's a few changes here and there, but many bits are the same. So what's a data structure? This is a bit more than an algorithm. We also have a notion of state, and we have a notion of some things that are kept over time. So in an abstract sense, it's a rule for encoding data, and the data structure specification will have to tell you what data means. So it's a way to encode something in computer memory, in binary at the end of the day. Plus, it's a set of algorithms to work with the data, either query it, ask questions about it, or modify it, update operations. If you've seen a data structures class or algorithms class undergrad, then you would have seen a binary search tree, I hope. That's one standard example, and we'll cover more. So the unit 2 will be a basic recap of some of these data structures that many of you will have seen, but we'll recap them quickly so that everyone's on the same page. Okay. Now that we've set the term straight, we can start with the real bit of this unit. In the next subsection, we'll talk about algorithm analysis. So again, getting at how fast is an algorithm as opposed to just does it get the right answer at some eventual point in time. So why do we do this? Often when we have some algorithmic problem, there are different ways to approach it, and we would like to find a good algorithm for it. And if there are several, we want to compare them. Now, what good means depends on the application, but most of the time it's being fast. So finishing the job earlier is usually our main criterion. And sometimes space is a concern as well. Space often has this weird behavior. If you have enough, it doesn't matter. But if you're out of space, you're completely screwed. And so it's a bit of a threshold thing. If you can expect an algorithm to take too much space, you have to worry about it. If you expect it to be fine, then time is the main criterion. I already said we want to compare different algorithms. There's a second goal of algorithm analysis, and that's, if you think from an engineering perspective, to predict how long something takes in a concrete application. We'd like to be able to do that so that you can estimate if some approach that you have in mind is viable or not. It's a very basic thing that engineers do all the time. I guess in programming and computer science, it's a little less needed than elsewhere because we can iterate faster. Often it's enough to just build it and check it. But there are cases where this is not good enough. If you plan a big enough system or plan an entire architecture, you have to know roughly how long will things take, or is the resource consumption within the boundaries of what's doable. It can also become a cost question. Everything's moving to the cloud, so computation often means dollars at the end of the month on your AWS bill. So it's definitely relevant to make a proper prediction of that. One obvious way to do a comparison of algorithms is implement it and run it. As I just said already, it has a few shortcomings that in various ways can be a problem. You have to know relatively well what you're going to do at the end with your algorithm or with your implementation. Otherwise, you can't get proper test data. That could be a real problem. If you're building a service that gets data from a client, you don't necessarily know what's coming. So all the results you find with running time experiments or running time studies are valid for the machine you tested it on, are valid for the concrete implementation you tested, for the inputs you tested. And all of that might not be what you eventually have. Also, that's back to the university lecture and the university course. This is not really universal truths. If you run it on your laptop and you get one result and your colleague runs it on their laptop and gets a different result, it's not ideal. And also, this doesn't sound like you can predict very well. So what we'll instead try is do mathematical analysis, where we have provable statements, but they hold in a certain abstract model, and we'll come to that. That's the main content for this unit. And hopefully from this, we can derive some hypotheses, which we can then test in an implementation whether they are satisfied. Because often these models make some assumptions. They simplify reality to a certain bit, and you can try to design experiments to test whether those simplifications are justified. As I said many times, the hope is that this is a way to get beyond the current iteration of technology in hardware, software stack, all these things. Things keep changing, and so doing something that's only valid today is not as valuable. What this means is we need precise models for all the things that are involved, namely the machine that things are run on. Already you have lots of machines with you, and they're quite different. Phones usually have an ARM processor, and laptops have some multi-cores. They have different architecture, different instruction sets, different operating systems, of course, as well. So they vary a bit. We have to bring all that down to a unified model that hopefully captures the main aspects. And we'll also have to model the input data. Remember, algorithms is input to output mappings. And lastly, what are algorithms? That's part of the model as well. Let's start with the easiest, because we'll usually stick to the most basic one here. That's the models for what input data looks like. The traditional ones in algorithm analysis are these three. Either you're pessimistic and you look for the worst possible input for your algorithm, or you're optimistic, you hope for the best, or you're the random guy and you look for the average over some distribution over the inputs. The average performance might be most realistic. It's harder to compute though. Best case performance is a little dangerous unless you can justify that this is to be expected. So in theoretical computer science, people study mostly worst case assumptions. And the simple reason is if you can prove that your algorithm is good in the worst case, you're fine, because that's the worst that can happen. It sometimes leads to overly pessimistic predictions. So sometimes you want to go away from that. But in a way, think of worst case as our default. And if we have reason to believe that this is unrealistic, that this is overly pessimistic, we'll try something else. We'll see a few examples of each of this. Now, if you think about algorithms, they're supposed to solve a whole class of instances of a problem. And usually these instances have a natural notion of size. If you think about a sorting algorithm, it's clear that if you make the list much, much longer, it's kind of obvious it has to take longer to sort it. Whereas if the list is 10 elements, you can probably do it manually. So there needs to be some way of saying the analysis takes this into account. It can't make sense to say, oh, the algorithm always takes X seconds. That's a lie almost surely, because if the input grows, the algorithm will take more time just to read the input. So what we'll do is assume some notion of input size, and we'll always call that n, pretty much always. So little n is a measure for the size of the input. And part of the data model is that you have to specify what the input size is, but is usually quite clear. So for arrays, it's the number of elements is a natural thing. For strings, the length of the string can be natural. For a matrix, it could be the total number of entries. For a graph, it could be the number of vertices or the number of edges. It's usually quite clear what makes a reasonable estimate for the size. And then we'll apply each of these data models for inputs of a fixed size. So we fix the size, and then we take the worst possible input for all of inputs of that size. That's the standard model. What this means is all the statements we're making, how fast is an algorithm, you can't really say fast or slow. You have to have a function that depends on the input size. And most algorithms will get slower as the input gets bigger. So the question is, how much do they get slower as the input gets bigger? That's why we'll study asymptotics at the end of this unit. Asymptotics will have to wait for Wednesday, but we'll talk about the machine model. And for that, I can also already start the Slido question. OK. Looks like the internet is back to normal speed compared to last week. In the next subsection, we'll look at our basic machine model that we'll use for most of the module. And that's the random access machine model, called the RAM model for short. to motivate a little bit of some of the complications I'm about to mention, let's do this little question of essentially jumping ahead of ourselves. So this already is talking in terms of asymptotic costs. What's the cost of adding two integers? Question? Well, we'll discuss it. Don't spoil the questions. So we had 63 vote for the attendance code. So we should get at least 60 again, right? And you remember, like, it's participation marks for Slido, not getting it correct. This might be the first question with an actual correct answer. So yeah, let me reiterate. It doesn't matter if you're voting for something that's not the correct answer. Okay, results trickle in. 59, that counts as 60. Good. Okay, so we have votes for most of the answers, right? And this is somewhat intended. Well, maybe there's no intention to have your answer for the last one, but if that's what it is, that's what it is. Try to lock that now. So there's, as you may see on your devices, there's a lot of correct answers. The problem is it depends on your model. It's a bit of a, well, religious question. What do you believe about your computers? You can argue it's constant time. Yeah? Let me run through this because we have to get through this in time, but we can take it offline. So there's an argument to be made for each of these answers. You can say it's constant time because, you know, my computer has 64-bit integers. I can add those two up in 1 or 2 cycles. That's constant time, isn't it? You could also say, well, hold on. If I give you two 20,000 digit long integers, good luck with squeezing them in your fixed size integer. Either you have overflows and you just get garbage results, or you'll have to spend more time. And if you just do the elementary school method of adding two numbers, you're basically going digit by digit in one way or another, carryovers and so on. So that takes time proportional to the length of the digits or the sum. So that's the answer in general. Okay, the last one is also correct in a way, but yeah. The point really is there's no good answer to this unless you tell me more. What integers? How big are they? What's the machine? Now, machine models are trying to put all these questions on a solid ground and make sure you can answer those definitively. So a machine model has to tell you what algorithms are possible, also because it specifies what programs are. So it sounds like it's just the machine, but it really is more than that. It's more influential if you want. And the last bit is important. This implicit in real machines, they just run, and as long as they run, that's the time cost. For our abstractly defined machines, we will have to say what is cost. What is the cost of an execution of some program? So we have a bit of conflicting interests here. We want machine models that are as detailed and powerful as our actual machines because we want to be realistic. At the same time, we want to not have one model for each computer in the room. We'd like to unify that if anyhow possible. And then we'd also like to analyze it, which again pushes it to the simple direction. And well, I don't know. I thought in terms of trade-offs, I don't know if you can laugh about this. So you usually can't have all three. Pick any two. Yeah, you can be smart, honest, or investment banker. Yeah. Is not too serious. But let me introduce the random access machine model before we close for today. The random access machine is basically one big array with operations on it. Now, the fun is the array is basically as big as you need it. It's not infinite, but it's unbounded. It's as big as you use it if you want. You can think of this as whenever you need more memory, you build more disks. That's not quite how computers work these days, but it's also not so far away from it. And cloud computing brought us even closer in some ways. The problem we're having at this point is we try to describe algorithms that solve, remember, a whole class of problems which have an input size. And the inputs can get bigger and bigger and bigger. So if we want a machine with an algorithm that can solve all of those, we'll have to allow arbitrarily big inputs. And that's only really possible if we also allow arbitrarily big resources, in particular memory. There's just no way around it. No fixed machine allows that. But if you look in history how machines got bigger, there's definitely some truth to it. Question?
Yeah, previous slide told that machine model decides on execution cost. So does that mean memory or the time?
Okay, the question is, well, what's the execution cost? I didn't get to that yet. So I first want to talk briefly, running out of time, I think. I want to talk briefly about what programs look like on this machine. And the cost will actually just be the number of executed primitive instructions. So that's relatively easy. As I said, the machine is one big array. What goes in the array? Well, integers. But we've had this question before, so you should all be asking, how big are the integers? And here the catch is, we'll leave that open. We say they have W bits. And W is not fixed per se, but can grow with the input size. So a typical thing is this, that W grows with the logarithm of the input or some multiple of that. We'll come to why that's a useful thing. But if you think of one big array, then log n is roughly the number of bits you need to specify one position in the array. And it just turns out to be both realistic and convenient to assume that one index into the data fits in one word. The content of the memory we call a word. And so W-bit words means each cell in the array can store an integer of W bits. The operations that fill up most of the slide, they're actually not too complicated. So you could do 3 types of things. You can get a memory cell and copy its contents to one of your registers. Haven't talked about registers, haven't I? You have a fixed number of registers that you can actually compute with. The memory is out there, and you have to get all the data into your registers, then you can compute, and you can write it back. And here for the registers, again, I don't want to fix a concrete number. So in a way, you can say if you need 5 more, that's fine. But it's a fixed constant number. The number of registers does not grow with the input. So you can say 100. That's usually enough for programs. That would be all right. If you want to compute, you can do this with the registers. You can do the normal type of arithmetic. Everything is done modulo 2 to the w, modulo the word size. That's how computers work. This is basically C-style operations. So you can do plus, minus, multiplication, integer division. And you can also do the bitwise tricks that languages like C, Java, Python, they all have something like this. So you can do bitwise AND of the numbers, treating the binary digits as individual bits. And left and right shift, okay, they're basically multiplications, so we wouldn't need those. Okay, that's the operations you can do in the register. Second type of operation is load something from the memory into the register and store it back. And you could do this by specifying the address with one of your registers. That's an important bit. That means you can do pointers and indirect addressing. Okay? And the last bit you can do is ifs, basically. You can condition on the value of some register. Is the register 0? If so, then jump to 5, skip to the next 5 instructions, something like that. And then the cost of a program run is just the number of instructions that you needed. This is a super low-level kind of machine and way to program. There's a book that describes this in a bit more detail if you feel like this is still having some gaps. The key thing I want to point out again, this is essentially programming in C or some other low-level language, except for this weird idea that the word size, the size of the integers you can work on in constant time grows with the input. Okay? We'll usually not code in exactly the primitive instructions. We'll allow ourselves the kind of high-level code I've shown you in the first lecture. There's a way to map that high-level code to what we've seen just on the last slide. It's usually very primitive, very automatic to do. In fact, compilers are exactly doing that. So we'll usually allow ourselves to be more convenient for human readers. I think you've seen all these. So we use the usual kind of control flow constructions as you would use them in Python. We allow ourselves to use variable names instead of just indices of registers and so on. And last important bit, we'll count dominant operations. So we'll fix some more abstract things to count instead of all primitive operations. That's often sufficient. One last comment before I let you go. We'll have to worry about memory management. So we assume that there's some way to allocate memory. And that's pretty much all you need to know about this for now. So we'll ignore how this is done. We'll just assume that this works. For most of it, you can pretend we're programming in C, just that we have these variable size registers or variable size words. All right, see you on Wednesday.